Okay, so this is where we left off last time. We're part of the way through this problem. And so determine the pH after 15.75 milliliters of HCl is added. Remember, in this case, we have a strong base. We're adding strong acid to it. Okay? And so what we're going to be doing here is, again, this is just figure out the moles, take the difference. Okay? Now, you don't actually have to get it the right way as long as you understand which one's in excess. Does that make sense? So if you know the one that's in excess, you can do the problem there. It doesn't actually matter which way you do it. So we're going to take that liters of NaOH here. Again, that's just the milliliters here, divide by 1,000 times the molarity here, because that's moles over liters. That will give us our moles of NaOH. We take the 15.75 milliliters, get that into liters, and again, multiply that by molarity, and that gives us our moles of HCl. We take the difference between these two numbers, and that's going to give us our remaining moles of, in this case, NaOH, right? Because we have extra NaOH that still remains. We'll take those moles of our NaOH, we need to divide those by the total volume. The total volume in this case is going to be the 35 milliliters plus the 15.75 milliliters, divide by 1,000 because those are in milliliters, we need them in liters. We divide by that number, we get the molarity of NaOH. When we want to find the pH, when we have the molarity of a strong acid, or a strong base in this case, then we're going to take the pH is going to be equal to 14 minus the negative log of that concentration of our strong base. So we plug our strong base concentration in here, take the negative log of it, subtract that off from the 14. Now, did I already tell you guys that you could do this in milliliters? Yeah, if you just put milliliters in here, you'll get millimolars. And then if you divide by milliliters here, you'll get back into molarity. It'll be fine, doesn't make any difference. And you can actually use prefixes as if they are components of your equation. Like millis cancel out just like any other unit. Okay? Did you guys realize that yet? No? Okay, cool. Well, there it is. If you want to see how that works out, by the way, let me know. I can post a little video. But it literally is just use them like units, and they'll always work out. Okay? So the millis, kilos, all those are just, you can use them like units. So determine the volume of the HCl that is needed to reach the equivalence point. Okay, so this is a little bit different. Normally we would have been like, what's the pH at the equivalence point? But we already know that. We've already discussed that, right? pH 7 for a strong base and strong acid combining together and neutralizing. So we need to get now the volume of HCl to reach the equivalence point. Well, to do that, we need to figure out how many moles of the NaOH do we have. And then we need to go ahead and take that and go, well, how many liters of HCl would we need to equal that number of moles, right? And so we've already calculated out the number of moles of NaOH. We actually did that in this previous problem, right there. See that? Okay. And so we take that number of moles. To neutralize that amount of NaOH, we need the exact same number of moles of HCl, don't we? And so that's the number of moles of HCl we have to get to. If you have a molarity and a moles, well, all you got to do is just take moles, divide it by molarity, because molarity is moles over liters, right? And that will give you your liters of HCl. And so we just take this number, 0.15, we divide it off of 0.0063, and we get our liters of HCl. And ta-da, that's the volume right there. Anybody have any questions so far? Fantastic. Yeah, please do make sure you practice these fairly soon after. They're actually really easy problems, but they're very easy to forget too. So determine the pH of the solution after 43.25 milliliters of HCl solution is added. This is actually kind of interesting because there's a couple ways we could go about this. There's actually quite a few. We've already done one way of doing this. I'm going to actually show you a different way of doing this, okay? So if you know your equivalence point, well, that's the amount that it takes to neutralize it, right? Your moles are equal at that point. So any amount beyond the equivalence point is excess, isn't it? So 42 milliliters of HCl, that neutralizes all your base. So that extra 1.25 milliliters, 43.25 versus 42, that extra 1.25 milliliters, that's your excess HCl. That's all the acid that's in your system. Okay? And so we take that 1.25 milliliters, we go ahead and multiply it by the molarity. We need to divide by 1,000 because we want it to be in liters, right? That's going to give us our moles of HCl. That's in excess. Now, in this problem, we actually have a dilution occurring here. I'm going to do the dilution as a two-step problem, but you could have just taken M1V1 equals M2V2. Yeah. So you literally could have just taken the 1.25 milliliters of excess HCl times its molarity and then divided it by the total volume in milliliters, right? That would have worked just fine. Okay. But conceptually, people get lost. So this way you can't get lost, okay? Which is that I take then the moles of HCl. I'm then going to get the total volume by adding all those volumes up. And so I have 43.25 plus 35. That gives me my 78.25 milliliters, or divide by 1,000 liters, right? And then I go ahead and take the moles over liters. That gives me my molarity. This is of the strong acid. And so to get pH, all I have to do is just take the negative log of that concentration. And that gives me my pH. Okay. And that's 2.62. And again, always double check. 2.62, that actually makes a lot of sense, doesn't it? We have a bit of strong acid left over. Yeah. Okay. So the next part we're going to be doing is we're going to go ahead and titrate weak acids and weak bases. Typically, these are going to be a weak acid being titrated by a strong base and a weak base being titrated by a strong acid. Okay? And again, they are actually just flipped relationships to each other. Remember how the strong acid, strong base stuff was just flipped? Yeah, same sort of thing. So this right here is the titration of a weak acid with a strong base. You'll notice several different regions here again. We have this part right here. Notice that's that initial weak acid, right? Anybody note anything about that pH? Is that like a 1, almost 0 number? It's up about 2, isn't it? It's a little higher, isn't it? What's true about a weak acid? Does it completely dissociate? No, you're going to get as much H plus out of a weak acid as you would a strong acid? No. So your pH tends to be a bit higher for weak acids, okay? You start at a higher point. Your B region. So in B, I'm going to be taking a base. I'm going to be neutralizing a part of that weak acid, right? And so when I have a pair of a weak acid and its conjugate base, does anybody know what that's called? There's a whole series of sections we've talked about it. It's called buffers. It's a buffer, right? So when I put a weak acid with this conjugate base in anything resembling equivalent amounts within 100 of each other, I have a buffer system, don't I? Okay? And so what am I doing here? Well, as I go and neutralize, I'm going to be making more and more of that conjugate base, aren't I? And that means I'm going to end up with a paired weak acid and its conjugate base, i.e. a buffer system. Okay? And so in B here, this is actually a buffer system. Everybody see that? See how it resists pH change? See that? It grows very, very slowly up, doesn't it? And it takes a lot of milliliters to actually overcome it. Yeah, buffer system. So over here where B ends, this is where we break our buffer system. We've neutralized so much of the weak acid, we just don't have enough of it left to act as a buffer anymore. Okay? And so what we're going to see here is it starts shooting up relatively quickly. And this is going to reach C. C is where the equivalence point is, right? We've neutralized all of our acid. We're just left with conjugate base. Okay? Now, can anybody tell me something about C here? What's the sort of pH you're looking at? So pH of 7 is neutral, right? It's basic. Because instead of making a neutral compound, what are you making? You're making a conjugate base, right? The conjugate base of a weak acid is itself a weak base, isn't it? Has to be. Otherwise, it wouldn't be a weak acid because it wouldn't come back together, right? And so that means with the weak acids, the pH is never 7 for when it's equivalence point. It's always above 7, right? Because you're making a weak base. Okay? Okay, this part right here is where we have put the strong base to the point where it's actually just approaching the strong base. This is actually just purely a dilution problem at that point, right? Okay. By the way, did anybody know why I made you do this before I gave you the answers? How do you build up critical thinking skills? Yeah. And the most valuable parts of this course and any scientific course is this stuff, okay? Trying to use your brain and developing those pathways to think critically, think like a scientist, okay? And this is how you do it. All right, so the initial pH is higher. Your weak acids do not release as much H plus as strong acid, of course. Your weak acids with lower Ka values will have a higher initial pH value. Because remember, Ka, the lower the value, the weaker the acid, right? The smaller the value, the weaker the acid, meaning less H plus. There's an initial rise in your pH, and you can actually see this region just before B. See that right there? Yeah, you get initial whoop, really fast, right? And that's because at that point, you haven't not yet established your buffer system, okay? So the weak acids are going to be port-resisting pH changes until your pH is closer to the pKa value, usually within 2 units. Remember how we said the best buffer region is plus or minus 1 to the pKa? That's what you're looking at, right? It's not an effective buffer until you get plus or minus 2, and then it's not a really good buffer until plus or minus 1, okay? Weak acids with higher pKa values are going to have a higher initial rise in your pH. I'm going to again make you do some critical thinking. Okay, let me ask you a question. Riddle me this. C is when you have completely reacted all of your weak acid, right? So if I go 1/2 of this distance, 1/2 of the base added, how much of the weak acid have I reacted away to base? So if this is 100% reacted, half that distance is, what's half of 100%? 50%. If I'm 50% acid, then what do I have to be? 50% basic, yeah. So at this point right here, the conjugate base is equal to the amount of the weak acid, isn't it? Okay. Anybody remember the Henderson-Hasselbalch formula for buffers, which we're a buffer right now? It's pH equals pKa plus log of the base divided by the acid, right? If you take the same number divided by the same number, what do you get? You get 1. If you take the log of 1, what do you get? 0. Yeah, 0. And you can actually prove this to yourself if you want. Take anything to the power of 0, it gives you 1. Okay? So the log of 1 is 0. We would have a pH equals pKa plus 0. And so at this point right here, half of the volume to C here, what is that pH value? It's equal to pKa, isn't it? Yeah. By the way, all those pKa values, that's typically how they get them. Okay? That's the most common way to get the pKa values because it's quite easy to do and it gives you very accurate numbers. So the pH at your equivalence point has to be greater than 7. The weak acids do not release as much H plus as strong acids. The conjugate bases of a weak acid are going to be more basic than your counterions of strong acids by definition, because it would not be a weak acid if it did not have a reasonable conjugate base that has some real basic properties. The titrations of the weak acids have to have higher pH values at that equivalence point, so they have to be a greater than 7. The pH change near your equivalence point is going to be less abrupt. It's going to have a less infinite slope. Okay? Strong acids, strong bases, they're almost straight vertical at that slope, at your equivalence point. A weak acid is going to have a slope that is going to be lesser, less drastic. The weak acids with the lower Ka values are going to have more elongated and less abrupt titration curves. And so this is what this looks like, by the way. This is a strong acid, this is a weak acid, this is a weaker acid, right? And so what do you notice about this? Your pH with the strong acid for initial is lower, isn't it? So you start at a lower point for the stronger acids. And then when you get up to this value right here, which is your equivalence points, well, the equivalence point for the weakest acid is the highest, isn't it? Okay? And then for the stronger acid, it's this right here, which is lower, and for the strong acid is even lower. Now, what you see here is that the difference between this region B and this next region right here, it becomes very small when you have a very weak acid, doesn't it? Can everybody see it okay? Fantastic. Because again, this point right here is going to be the pKa. See how this point right here is 8 for this one? Because that's -8 up here, right? Okay, so an equal amount of each of the following weak acids is titrated with 0.1 molarity NaOH. Select the acid with the highest and lowest pH at the equivalence point. Okay, so the we're looking at the equivalence point. What is the equivalence point? It is where you have all conjugate base, right? So the highest pH is going to belong to the one that has the worst pKa, right? The weakest acid. Okay, so again, what direction does the weak versus strong acids go for pKa values? Is this a weaker acid or a stronger acid than this one? Yeah, this is the weaker acid, right? And so the order we're looking at here, and by the way, there's actually a hint in the names. If you just look at the names here, they tell you this. Would be the 4.2 right here, benzoic acid. That's going to have your lowest pH at the equivalence point, isn't it? This is going to be your next one, acetic acid, and the next one's going to be pyridinium ion. Notice, by the way, these two are acid. This one's called pyridinium ion. Did you notice that? Yeah, because this is not normally considered an acid, is it? Because of the fact that the pKa value is so high. Yeah. All right. So let's calculate the pH and the weak acid strong base titrations for the region A. Now, at this region, this is actually just an ice problem, okay? I'm going to show you quick and easy to use formulas for this that can really make your life faster. But to be honest with you, I never bothered memorizing any of this when I was in your guys' situation. Yeah. I just, if I happen to forget it or I couldn't derive it immediately, I just went back to an ice problem. It takes like half a minute to do an ice problem, right? Fine. I'll take half a minute extra. Actually, you can usually get them done a little bit less than that, right? Yeah. Oh, okay. Yeah, more practice will give you faster. But yeah, if you want to memorize formulas and that's your thing, this will speed that process up. Okay. So at the initial pH of the weak acid solution, usually you're going to be less than 5% change from that initial concentration, right? And so we can go ahead and make that 5% assumption we would in the normal ICE problems, where you don't have to minus x. You don't have to do the quadratic formula. And so if you make that assumption, you'd get a Ka that looks like this, x squared over the initial concentration of that weak acid, right? If you then take that and substitute that in, you would go ahead and get pH equals the negative log of the square root of the Ka times the initial concentration of that weak acid. And that's just your entire ICE problem collapsed down into a single formula. Okay? That's all that is. And again, if you do not remember this, it does not matter. All problems in these 3 chapters can all be done using ICE problems with an equilibrium expression, right? Okay, so this right here, the addition, this is the region B here. In region B, you're in a buffer region. And so the easy way to handle these regions is to go ahead and use the Henderson-Hasselbalch formula. So pH equals pKa plus the log of the base over the acid. Remember, this is again making the 5% assumption. And again, this is the initial concentrations. So if we go ahead and go to region C then region C is going to be where we have all conjugate base, isn't it? And so region C is just an ICE problem for the conjugate base. That's it. That's all region C ever is, which is again that equivalence point. So what we're going to do is we're going to take and get Kb. This is Kw divided by Ka. If we go ahead and then give us our next substitution, which is that ICE problem. So we took the bottom part of that ICE problem, made the 5% assumption. This is going to be x squared over the conjugate base here. We can go ahead and simplify this further, going, well, we want x. X would have been the concentration of OH minus. That's going to be the square root of Kb times the initial concentration of our weak base here, the conjugate base. We go ahead and go, well, normally we want the pH for these things, right? And so we take the pH formula, 14 minus the POH, and we go ahead and we can substitute that in. And so we're going to say, hey, we're going to end up taking that 14 minus our negative log of this OH minus concentration slash X. Okay? And so you can very quickly go back and forth. Notice, by the way, here, this square root Kb times the conjugate base here. Do you see that? Notice region A. The square root of Ka times the concentration of the acid, right? It's actually the same formula because it's the same ICE problem, just one is for a base, one's for an acid, right? Yeah. Okay. When you're past the equivalence point, your pH is just straight up going to be the concentration of the base that you've added. Okay? And so what you're looking at here is your excess base diluted. Now, the simple way to do this is to do a dilution of that concentration of the excess base you've added. Plug that into the 14 minus the negative log of that concentration right there. All right, so let's go ahead and try this. So suppose that 40 milliliters of 0.5 molarity formic acid, which K is this value right here, we're going to go ahead and assume that the X is less than 5%. Okay? That solution is titrated with 0.5 molarity solution of NaOH. So prior to the addition of NaOH, now normally we would do an ICE problem for this, but I've given you simplified calculations, right? And so we're going to go ahead and plug that in and see how that works. Okay? So we take the Ka here, 1.8 times 10 to the negative 4, times the concentration of formic acid, that initial concentration, 0.5. Again, this is valid because we're assuming that X will be less than 5% of that initial concentration. We take the square root of that resulting number, and we get the negative log of that. That will give us the pH, which is 2.02. Now, at half the equivalence point, what are we looking at again? I made you do this before showing you the formulas and proof of it, because I wanted you to be able to think problems through and not become an absolutely useless parrot of Dr. Clausen who can't do anything else. Okay? No matter how smart or great I am, yes, you do not want to be a parrot of me, okay? You need to have your own stuff, your own life. All right, now, again, this is going to be the Henderson-Hasselbalch formula, pH equals pKa minus the log of the HA over A minus. Again, if we take the pKa, if we take the same value for the acid and base, that would give us a value of 1, right? So the same value over same value gives us 1. Doesn't matter what those numbers are, whether they're 1,000 over 1,000, 100 over 100, right? And the log of 1 is always 0. So this term never matters at this equivalence point, half the equivalence point. Now, the pKa is going to then equal the pH at half that equivalence point. And so what we're going to then have is the pH just straight up equals the pKa. So we just take the negative log of that Ka, 3.74, that's our pH. All right, so at the equivalence point, we just need to calculate this as if we had all initial concentration of the conjugate base, okay? And so what we're going to do then is we're going to figure out the initial concentration of that conjugate base. We do that by taking 40 milliliters right here times the 0.5 molarity divided by the total volume. Now, the total volume in this case is pretty easy to calculate. And the reason for that is this has the same molarity for the NaOH, right? And NaOH is going to have a 1-to-1 ratio to neutralize the formic acid, okay? And so the volume that you need to neutralize that formic acid, that's just the same volume you put in for the formic acid, isn't it? Okay? And so it's just 2 times 40. That's your total volume at this point. And so we take 40 milliliters times 0.5 molarity divided by 80 milliliters. That's going to give us the 0.250 moles over liters. This is the concentration of your initial concentration of conjugate base. We also need to get the Kb. The Kb is going to be 10 to the negative 14, i.e. the Kw, divided by the Ka, which is 1.8 times 10 to the negative 4. And that gives us that 5.6 times 10 to the negative 11, which is our Kb. We actually have all the numbers we need now to use the quick and easy formula. So to get the POH, we're going to take the negative log of the square root of the Kb times the initial concentration of that conjugate base. And so those are our numbers right here. Multiply, take the square root, then take the negative log. We get 5.43. Remember, that is the POH. To get the pH, we need to take 14 and subtract off that number, right? And so that gives us the pH, which is 8.57. That makes sense because this is the equivalence point of a weak acid. And those are always greater than 7, aren't they? Okay, so when the equivalence point has been reached and we add 2 milliliters of excess NaOH, well, this is actually just a dilution problem, isn't it? Yeah. So at this point, we're just diluting this excess NaOH. And so the OH minus concentration, that's just the 2 milliliters times the initial concentration of the NaOH, which is 0.5. We were at 80 milliliters. We added 2 more milliliters. That gives us 82 milliliters, doesn't it? And so 2 milliliters times 0.5 molarity divided by 82 milliliters. Notice that's just M1V1 divided by V2, isn't it? Which is the M1V1 equals M2V2 dilution formula. And so that gives us our concentration of OH minus, which is 0.0122 molarity. We need to go ahead and take that, and we need to get the pH from it. So we're going to take 14 minus the negative log of that concentration. That's going to then give us our pH, which is 12.09. That makes a lot of sense because we just add some strong base to this already basic solution, right? Anybody have any questions about that? Fantastic. So this is going to be the weak base where we're adding the strong acid to it. Now note that this is almost the exact same sort of thing as the weak acid, adding strong base to it, okay? The only difference is we flipped it on its head. And so the initial pH is going to be basic, it's not going to be acidic. The pH area equivalence point, this is acidic, not basic. We're going to be a pH below 7 now at the equivalence point. Because remember again, a weak base is a weak base because its conjugate acid is itself a weak acid, isn't it? And so the pH at half the equivalence point, this would be equal to the pKa of the conjugate acid of your weak base that's being titrated. The pH is going to be acidic, not basic, the final pH, because you'll have excess strong acid at that point. Okay, and so we can see that this is literally just the previous curve flipped on its head. See that? Okay. And so again, we have that A where we have the just weak base, and this is just the isoprom for the weak base. We have B, it's a buffer region where we have the pair of the weak base and its conjugate acid. And then we have C, the equivalence point, has to be a pH less than 7 because we've made all weak acid at this point, haven't we? And then D is just a diluted strong acid. Okay? The excess strong acid is just being diluted and eventually getting back to its concentration. Okay, so let's suppose 20 milliliters of 0.15 molarity solution of ammonia, and there's ammonia, NH3. The Kb is 1.8 times 10 to the negative 5. Again, we're going to assume that we're less than 5% for our x, so we can make those base assumptions and do this problem the easy, quick way instead of quadratic formula way. The titrated with 0.2 molarity HCl. Determine the pH at these points. Now we've actually thrown something into this problem that's going to make this mathematically just slightly harder, isn't it? And that's the fact that this is 0.2 and this is 0.15. See that? So it's no longer a 1-to-1 ratio, is it? Yeah. It's not the same concentrations. So let's get the pH prior to addition of the HCl. So in this time, we're going to get the POH. This is going to be using that quick and easy formula, which is the negative log of the square root of Kb times the initial concentration of the NH3. So we go ahead and take the negative log of the square root of the 1.8 times 10 to the negative 5, which is our Kb, times the initial concentration of our base here, which is 0.15. This is a POH of 2.78. Again, that's not a pH, it's a POH. And so we need to subtract 14 by that number, don't we? And that gives us our pH of 11.22. It's basic, we have a base. That makes sense. We're looking pretty good. Okay, next is going to be half the equivalence point. Okay, so remember how the buffer regions, we typically do these in Kas, right? So pH equals pKa plus the log of, and then we can ignore that part because we're half the equivalence point already. So it's going to be, same number over same number, log of 1 is 0. Okay, and so what we need to do now is, we don't have the Ka, do we? Yeah, we need to get the Ka. So we're going to take Kw divided by Kb, so 10 to the negative 14 divided by 1.8 times 10 to the negative 5. We're going to take the negative log of that to get the Ka. So the pKa of this is going to end up being 9.26. That number is going to be equal to the pH because we're half the equivalence point. And so we now have our half equivalence point pKa number, don't we? Very nice. And again, this makes sense because we're still above pH 7, aren't we? Yeah, we haven't neutralized this thing. Okay, we at the equivalence point. So at the equivalence point, what's going to happen is you're going to convert all of your base, your weak base, into weak acid, aren't you? Okay. And so at this point, what we're going to do is we need to figure out the initial concentration of our weak acid that we will have generated. So we have 0.02, that's the 20 milliliters right here, times the molarity, which is 0.15 moles over liters. This gives us our moles. That will be the weak acid. We then need to get that number back into the volume. And so to neutralize that amount of our base, we need a similar moles of the HCl. And so what's going to happen here is we have the 0.003 moles, right? To get the neutralize that, to react all of this away, we would need the same moles of HCl. And so we take that number of moles of HCl, we divide it by the molarity, that gives us the volume of HCl we had to have added. Okay? So now we have moles of our weak acid, and we have the volume of it that was added on the two areas. So we have the 20 milliliters and the 15 milliliters here. And so what we're going to do is we'll take the moles of our weak acid, divide it by the total volume, which is 20 milliliters plus 15 milliliters. Those need to be divided by 1,000 to get liters, of course. And that gives us our molarity. Okay. Did I get anybody lost there? Nope. Okay. So again, this is still at the equivalence point. We are going to again be looking at that weak acid. We now have the initial concentration of it. We also actually have the Ka of it. Because remember, we took the Kw divided by the Kb before. That was that Ka. And so what we're going to do now is we'll use that quick and easy formula, negative log of the square root of your Ka times that initial concentration we just figured out right here. Okay? And then that's going to give us a pH of 5.16. Does that number make sense? Yeah, it's just a bit below 7, isn't it? Yeah, so that number makes a lot of sense for the titration of a weak base. So when the equivalence point has been reached and 1.2 milliliters of excess HCl has been added to the solution. So remember that this is again just a dilution problem. We have an excess 1.2 milliliters of the HCl. We're diluting that down because now we're putting it into a lot more volume, aren't we? And so we're going to take that 1.2 milliliters times the concentration of the HCl, which is 0.2, and then we'll divide it by the total volume. And the total volume here is that 20 milliliters plus 16.2. Okay? And again, you could have also just taken the total volume from here, by the way, and added 1.2 to it. That also would work if you had written it down. All right, so that's going to give us our molarity now of our HCl. That's 0.0066. We just take the negative log of that value, and that will give us our pH. And our pH is 2.18. And that makes sense. We have some strong acid we've added to the solution nowadays, don't we? So we'd expect a lower pH. Okay. So let's look at the titration of a polyprotic acid. So when we look at polyprotic acids, how did we look at them? Did we look at them all the hydrogens coming off in one step? We look at them one at a time, don't we? One H plus coming off each step. And so many of these weak acids do have more than one ionizable proton, meaning a polyprotic acid, right? And there's a lot of these polyprotic acids are incredibly important biological species. So they have an extra level of importance to them. So things like amino acids, nucleic acids, phosphate, you guys probably have heard of these things before, right? DNA with a phosphate backbone. Why do you think an amino acid is called amino acid, by the way? It's an acid, isn't it? Yeah, it has an amine and an acid, right? So the diprotic malonic acid here, this actually has the two following equilibriums where we have Ka1 and Ka2 coming off. Everybody see that okay? Okay. And so what does that tell you right there? Well, that tells you that if you titrate this, you're going to have two sets of titrations, one stacked on the other. Okay? because you'll have two buffer regions that you make, right? You'll have two equivalence points. One where you've made and converted all of the malonic acid to its conjugate base. One where you've converted that conjugate base to its conjugate base, right? And so right here, we actually see the titration curve of that. So please look at that real quick. Appreciate that. Can everybody understand the regions here when you look at that? Initial concentration, right? What region is that? That's the buffer region. That's the buffer region for that right there, isn't it? So that's the Ka you would use for that buffer region. We get up here, what's that? That's the equivalence point, right? What happens at the equivalence point again? We've converted all of the acid to the base, haven't we? Yeah. And so at that point, we've converted all of this acid here to this conjugate base right there. Okay? Now, at that point, we have the first conjugate base, don't we? We have the first deprotonation done. Okay? And so what happens at this second step is just that first deprotonation is done. We just take that species right there and we deproton it one more time, don't we? And so now we're at the initial concentration of our second deprotonation acid, aren't we? Okay. And then we go into another buffer region, and then we go into another equivalence point, don't we? And again, all of those buffer region equivalence point, they're just dependent on that Ka2. Okay? And so at that point right there, we have generated all of our species in this solution as being that, which is the fully deprotonated conjugate base. And then after this point, we're just adding excess strong base, aren't we? Okay. Okay, everybody see that, appreciate it, can understand when you look at that? This is probably the easiest way to understand titrations, by the way. If you just sort of envision them as titration curves. Okay? What would a triprotic look like? You'd have 3 steps, right? Yeah. You just have 3 equivalence points, 3 buffer regions. And they all end up with excess base coming on it, right? There you go. Yeah. Okay, so let's talk about indicators in acid-base titrations. This is, funny enough, kind of one of the most misunderstood and most screwed up things. So an indicator can be used to determine the equivalence point of a titration. Most of the indicators used for acid-base titrations are going to be weak acids, where the protonated acidic form is one color and the unprotonated basic form is another color. And you can think of your phenolphthalein indicators, or you guys said you used... was it last week you guys turned orange? Okay. There you go. Okay, so that was probably like a methyl blue, the blue one. And the orange one was probably methyl orange, right? Yeah. Or you guys were using universal indicator. Which is the same thing, it's just they mixed up. Okay? So this is what was happening in those cases. So you have what is a weak acid, right? A weak acid is also a weak base, isn't it? See that? When you deproton a weak acid, you get a weak base, right? And indicators are simply acids that are one color when they have the proton on them and a different color when they have the proton has been lost. That's all they are, okay? It's really that simple. Now, there are a handful of indicators that are quite interesting because they actually have different colors and they're diprotic. Okay? So again, we're going to have one color when we have the proton on it, one color when we have the proton off. Phenolphthalein is probably the most commonly used one. It's that pink one. Remember clear to pink? Where I showed you that video and you probably saw it in person at some point. So this is the commonly used strong acid, strong base titration, and it's because it's colorless in acidic solutions, and it turns a pink color over pH 9. It's actually 8.4 that turns pink. Now, this is, again, that equilibrium. We'll have one color. It deprotonates. We have the second color. Now, when can you actually tell the difference between colors? If I put one drop of blue dye into the ocean, not blue, let's use, what color do you guys want to turn the ocean into? Yellow? Okay. Okay, I put one drop of yellow food coloring into the ocean. Is the ocean yellow? Why isn't it yellow? You got it. And so if I have a dye and 99% of it hasn't turned color, is it going to look that color yet? No, I can't see, right? And so typically what happens is you turn colors when you have a 10 times concentration difference, okay? And so it will be the color of A minus when there's 10 times more of that than HA. It'll be the color of the HA when it's 10 times more HA than A minus. Is that making sense? Okay. And that's how you can tell the difference between colors. By the way, one of the reasons why you have some of the, like phenolphthalein is very popular is because it's clear and then colored, right? You guys use methyl blue? Yeah. Blue, yellow? Blue, green, yellow? Did you guys ever get yellow? Yeah? Oh, okay. Okay, so what's happening there? Okay, so what's actually happening is it's blue and yellow. It's not green at all. Do you know that? What color do you get when you mix yellow and blue? You get green. Yeah, and so what you're doing is you're actually going from one and you're getting it halfway between, that's green. And then you're getting it all the way to 10 times, and that starts turning more and more yellow. Okay? Okay. And again, those limits are actually somewhat arbitrary. You have a lot of error in your eyes, okay? And your ability to detect those colors. That's why if you want to do it really well, you'd use visible light spectroscopy. So the color change of an indicator, i.e. your endpoint for a titration, this is actually going to always be different than the equivalence point of a titration. Like, for example, has anybody ever tried to stop a car when exactly on a line? No? So you can set up for a race? No? Okay, do you know how you actually do that? You put blocks at the line, and then usually they're towed up to the block. Yeah. By like something very slow that can do it very exactly. If you ever try to stop a car on line, what happens? Yeah, you're always going to screw up, right? You can't do it. It's just not possible. And so the indicators have fixed points that they're going to be visible to change color, and these points are basically never on your endpoint. Okay? Or I should say they're never on your equivalence point. So every time you do these titrations, you're always ending the titration at a point that's a little off, okay? And so the pH change is very rapid at your equivalence point, and this is what we're taking advantage of to make this error not just awful, okay? And so what we're doing is, here's the equivalence point, right? The equivalence point is when the moles are equal. And so we hit the equivalence point, we add excess of the strong base in this case. This is going to cause us to get to a pH point that would be where it turns pink. And then we go, oh, pink, stop. And that's our endpoint, isn't it? Okay? Notice though, we are not at the equivalence point, are we? No, we're a little past it. In fact, we're not even at when it would have started changing color, right? Because we couldn't see that, could we? No. And so we end up at the endpoint up here, which again has some error to it. So phenolphthalein actually works quite well for strong acid-base titrations. For most weak acid and strong base titrations, it also works quite well. because again, that has that endpoint around pH 8.4 typically. However, if the weak acid has a very small Ka, the phenolphthalein may not be useful because the equivalence point could be after the pH 8.2, 8.4. Okay? It could actually be up in the pH 9s, right? In which case we would have been very, very far off. And so this may not actually be useful for those cases. It may actually need something that has a higher indicator range, that has an indicator range that would give us an endpoint to the pH of our equivalence point. Now, I'll go ahead and pick up from here next time. Okay. Remember that on Friday, we're actually going to pick up from the section where Thursday left off, okay? And I'll depend on you looking at those videos. This material is actually not that bad if you get it out of order. It's pretty well cut and dry, and you kind of already have all the establishing stuff. Yeah. You may notice it all kind of looks alike too. Yeah. Is anybody going, God, Dr. Clausen, please just get off of this ice problem equilibrium crap? No? Yeah. I was like that when I was in it. I was like about fifth of the way through the second chapter of ice problems, and I'm like, oh God, just please finish. I got it.